Hello, hello. So my name is Kacai Sakrawat, and this is the video for my laboratory test. So according to the matrix number, my voltage in my initial XYZ is 809 and my new XYZ is 209, meaning my circuit will be changed to 209 kilovolt. So now my circuit has been set to 80V, to 80 S base, and the bus has been set to 33 kilovolt. For bus 2, we have set the value of voltage to be 209 kilovolt. For bus 3, we also set to 209 kilovolt. And finally, for bus 4, we set to 11 kilovolt with 50 MVA. The H line over here is 100, has been set to 100, which is the series reactance. Transformer over here has been set to 1200 MVA limit. Okay, so now we run the circuit. As you can see here, this this is the value of our load at bus 2, which we got 34.2 megawatt and 45.6 MVAR. Since there is no shunt component, the PU, the power factor at bus 2, 3, and 4 is not at 1, and they are at 0.99, 0.98, 0.97 respectively. So the load over here is 12 megawatt and 9 MVAR. And there is significant voltage drop since the power factor is not completely 1, which is 206.98 at bus 2, 204.93 at bus 3, and also 10.68 at bus 4. So now we set the shunt component, and we will do the value until it reach 1 power factor for all of the bus. So this is the circuit with shunt component and at the value of 9.5172 MVAR. So here, as you can see, all the power factor are now the same, which is at 1, and there is no voltage drop across the transmission line. At bus 2, we have 209.03 kilovolt. At bus 3, 209.1 kilovolt. And finally at bus 4, which is 11.01 kilovolt. There is no voltage drop, and the load is also the same. So this is our table, as you can see, of without shunt. The nominal kV at the circuit without shunt is 33 at bus 1, 209 at bus 2, 209 at bus 3, and 11 at bus 4. But the actual voltage obtained is lower than that, which is 33, 206.9, 204.93, and 10.68. There is no changes in the angle, which is negative 0.09, negative 1.43, and negative 2.15. And here at the load, as you can see, is the same as our calculation, which is 34.2, 45.6 MVAR. As you can see from the calculation. here at PU load and at the load at bus 2, where we have to obtain the same result. And this is the table with the shunt component at 9.5172. And as you can see here, all the voltage are the same since the PU voltage have power factor of 1. The load stays the same. Generator megawatt and generator MVA also stays the same, except only the voltage output are different. This is the simplified circuit when the pre-calculation has been done, where we have 0.682 plus J 0.912 PU for the initial load, J.01 PU at XT1. At X line, we got 0.183 PU. XT2, we got also the same, which is J 0.1 PU. Finally, at the load at bus 2, we got 0.15 plus J 0.1125 PU for the final load. And here for our P power is we got 34.2 megawatt, and for Q we got 45.6 MVAR. This is the pre-lab calculation. So for the discussion, the primary focus of this laboratory was to apply the per unit system to model a power network containing multiple transformers and transmission line. And from the simulation result and also the pre-calculation, we obtain the same result, meaning the calculation has been done correctly and the circuit also is theoretically correct. And in conclusion, all the stated objective for this lab test was successfully achieved. Through the use of power board, the system was simulated to solve for the complex power delivered by the generator and to monitor bus voltage. The experiment confirmed that while natural system impedance led to voltage degradation, this level can be maintained within prescribed boundaries through the application of shunt component. This laboratory experience reinforced the importance of per unit analysis as a simplified modeling tool and highlight the critical role of reactive power management in ensuring voltage stability across a power grid.